quantum mechanics. All right, so let's start. So first we define an inner product space. So an inner product space is a vector space with an inner product structure that satisfies these properties. So one slightly different thing that we're going to do is that we're going to say that it's linear in the second term instead of the first term by the convention of physicists. Normally mathematicians make it linear in the first term, but we're not going to do that. So once we have an inner product structure, the inner product defines a norm on our vector space, given by the square root of a vector with itself. And so we call a Hilbert space, or a Hilbert space is an inner product space which is complete with respect to this norm. Okay, so an example of a Hilbert space is L2 of R. So it's a space of functions from R to C that are square integrables. So we take the absolute value of a square of the absolute value of the function and integral from minus infinity to infinity, and that's finite. So this is a Hilbert space. It induces an it has an inner product structure. Given below, you take the complex conjugate of the first term times the second one, and you take the integral. Okay, so now we're going to talk about linear operators. So a linear operator is a map between vector spaces that's linear. So it's defined on a subspace of X, and it satisfies these properties. So basically, for finite dimensional vector spaces, the linear operators are matrices, but for infinite dimensional ones, we have more. So so we say that a linear operator is said to be bounded if there exists a constant such that the norm of t times x is less than or equal to that constant times the norm of x. So this concept doesn't really come up in linear algebra because every linear operator is bounded in between finite dimensional vector spaces. So it's really only important again when we're talking about like infinite dimensional vector spaces. So we want to sort of generalize the idea of eigenvalues that come up a lot in linear algebra. So the generalization of our set of eigenvalues is the spectrum of an operator. To define the spectrum, we define the resolvent operator of our operator t. So the resolvent is for some complex number lambda. So we fix lambda, and we say the resolvent of t is t minus lambda times I inverse. So the point spectrum is the set of lambda such that our lambda of t doesn't exist. So the resolvent doesn't exist. In other words, t minus lambda I is not invertible. So that coincides with our normal idea of eigenvalues. The continuous spectrum is a set of lambda such that our lambda exists and it's defined densely in our space, but it's unbounded. So that's an important case for lambda. And then there's the residual spectrum, but I don't know if anybody really cares about that. I don't. So the spectrum is that is the union of these three spectrums. So that's the spectrum of an operator. What is this slide? Okay, so now we're gonna talk about the adjoint. So the adjoint of an operator, T is the operator T stars that satisfies this property, that the inner product of phi T psi is equal to T star phi psi. And so yeah, if our the domain of our operator T is dense in our Hilbert space, then we know that this always exists, this adjoint. But we are interested in the case when T is equal to its own adjoint. So so we call T symmetric if basically it satisfies this, if T itself satisfies the property that T star, we want T star to satisfy. But even if T satisfies this property, it might not exactly be equal to T star because the domains that they're defined on might be different. So, and generally it's actually an extremely non-trivial question to determine whether or not the domains coincide, but it's also an important question. So yeah, that's sort of hard subtlety. And that also only really comes up when we're talking about unbounded operators. Okay, so So one nice property that self-adjoint operators have is that the spectrum is entirely real. So this is a proof that for the point spectrum, that the point spectrum is real, but we have this generalizes to the other parts of the spectrum as well. So let's give an example of an operator between vector spaces. So we have the so-called position operator. So it's a linear operator from some domain to L2 of R. So the domain is in L2 of R. And basically what it does is it takes a function and just multiplies it by x. So yeah, it's a fairly simple operator, but it has some sort of weird properties. So first of all, it's unbounded. And a proof of that is just to consider this function. It's just 1 over x in some interval and 0 otherwise. And it doesn't really matter what the interval is, but the point is that it's sort of constructed so that the norm of this function is 1, but the norm of q times the function is n. So we can make that as large as we want. So q is symmetric. So this is a proof that q is symmetric because x is real. We can essentially just take it under the complex conjugate in this integral. So that's fairly straightforward. But what's not so straightforward to prove is that q is self-adjoint, which is actually, I don't think it actually is technically self-adjoint. It's called like essentially self-adjoint, but that's like good enough, I guess. And that's enough property. And the spectrum of q is the entire real line, and it's entirely continuous. So it doesn't actually have any eigenvectors. Okay, so now what does any of this have to do with quantum mechanics? So we're going to talk about the postulates of quantum mechanics. So this is basically how we model physical systems. So given a system, we represent our systems by vectors in some appropriate Hilbert space. So yeah, the vectors correspond to our physical systems, and scalar multiples of the vector we say correspond to the same state. For observables, like such as position, those correspond to linear operators from the Hilbert space to itself. And when measuring a state, the spectrum of the operator consists of any possible outcome for the measurement. And we get the expectation of the measurement, so the expected outcome of whatever we measure of our state is given by this inner product of phi with t phi. So, any questions about that? Okay, yeah. So an example is the states are an example of Hilbert space is L2 of R. The states in L2 of R represent the state of a particle on the real line. So the position operator corresponds to the observable, that is the position of the particle on the line. The expected outcome of given some state phi that a particle is in, when we measure the position, the expected outcome of the position is given by that integral, the integral of x times the magnitude of phi squared. So in general, if we want to know when a particle is in some subspace, so what the probability that when we observe our state, we find the particle in some subspace of our line, that probability is given by this integral, the integral over e of phi of x squared. So this is assuming that phi is normalized to 1. So the magnitude of phi of x squared is the probability distribution of our particle. So one sort of simple example is that, say we know for certain that a particle is in some one position, we know that for sure. Then that corresponds to the state delta of x minus lambda, where delta is a Dirac delta function. But there's an issue in that delta isn't actually in our Hilbert space. So, but we want this to be a valid state that that our particle can achieve. So so that can sort of be fixed by considering something called like rigged Hilbert spaces, but I'm not gonna talk about that. But yeah, and so the delta function, this delta of x minus lambda, can also be sort of thought as an eigenvector of Q, corresponding to some value lambda. And so this is just a quick argument that it can be thought of as an eigenvector of lambda. Okay, so so I've talked about the position operator a lot. So now let's talk about the momentum operator, which is in some sense the position operator. I mean, not really. Well, in a sense. So the momentum operator is the linear operator that takes a function and it basically just acts on negative I times the derivative of that function. So it has a lot of properties similar to the position operator, in that it's unbounded. The spectrum is the entire real line. It's defined in a dense subset of L2, and it's symmetric. So the position operator and the momentum operator don't commute, but they satisfy this commutation relation, which is often called the canonical commutation relation. So the commutator of Q and P is I times the identity matrix, or the identity operator. And the proof of that, just uses the chain rule. So it's a consequence of the fact that the position operator and the momentum operator don't commute, that we get this sort of famous uncertainty relation between P and Q. So where this delta of your operator is the so-called uncertainty of that operator, it's pretty much just like the variance, and what this relation says is that we can't, given some position phi, if we want to get information about a particle, like where it is on the line, we can't both know the position of the particle and the momentum of a particle to like an arbitrary degree of accuracy. It's always sort of bounded. So if we know the position of the particle to a high degree of accuracy, then we don't know the momentum. It sort of could be like pretty much anything. Yeah, and so so as I sort of mentioned before, the position and the momentum are sort of duals of each other. So right now, what we've been doing is we've been working in the momentum space of the position space, where phi is our position space wave functions. But there's also, and so given our position space wave function, we sort of know everything there is about the state of a particle. But we also have momentum space wave functions. So given a state in the momentum space, we also know everything there is to know about a particle, and we can sort of go back and forth between the position space and the momentum space with a Fourier transform of our state. So yeah, that's the formula for given a position space, we can get the momentum or the position space wave function. We can get the momentum space wave function, and vice versa with the inverse Fourier transform. So in the momentum space, the roles that the position operator and the momentum operator play are sort of reversed. So in the momentum space, the momentum operator plays the role as multiplication by constant p, and the position operator plays the role of the derivative with respect to p times I. And so the way that the position or the momentum operator is really defined is that it sort of generates translations. So it generates changes in position, which is an idea that can be made rigorous. But once we have this momentum operator defined, the position operator also satisfies the property that it generates changes in momentum. So there's a sort of a duality there, and apparently, so the duality between position and momentum is an example of pawn-dragon duality, which I don't know what that is, but I found out that it's a thing, so I put it in. Yeah. Okay, that's it.
Any questions for Kenneth? So, way back when you were describing the spectrum, you had a function, here, r sub lambda of t, and I was sort of wondering why you wouldn't make this a function that depends on t and then have lambda described there, and then this would be a complex value function you could apply as sort of like the like ideas of complex analysis to look at its poles. Something like that. Is there a reason why it's written like this?
So r sub lambda of t is an operator. So,
great, but if you swapped it so that t was fixed, and then you were just looking at as a function of lambda, then that would be a function which takes in a complex number and spits out. What would it spit out? I guess maybe a determinant for that. But
yeah, I don't know. I don't really know.
Yeah. It just struck me as kind of funny.
Yeah, it is kind of a weird way. I also thought it was kind of funny in that you're sort of defining the operator and then deciding whether or not it exists or something. I don't know. But yeah, actually, the way it's defined in whatever book I was using, Krasig, is like it's even more roundabout. It feels like it like I don't know. That's just my opinion.
Any other questions?
Yeah.
So for the position operator, it's kind of, you can see what it does by testing it on a delta function, right? You see it spits out exactly what a delta function is.
Yeah, yeah.
Is there an example like that for the momentum operator?
Yes. So the sort of the quote unquote eigenvectors of the momentum operator are let me just so e to the I lambda. So those are so yeah, negative I d rho or d dx e to the I lambda x equals lambda times that. But the issue is, again, this isn't actually in our Hilbert space because it's not square integrable. So
okay, but that helps enough.
yeah, okay, yeah.
If there are no further questions, then let's go ahead and thank Kenneth again. We'll be back here in about 7 minutes for our final talk of this session.
Yeah.